Okay, so thank you for introduction. And first of all, I'd like to thank the organizer for giving me this great opportunity to share my work with all of you. Okay, so today I'm going to talk about some important thermodynamic trade-off relations, so-called speed limit, and its application to finite-time Landauers bound problem. Can I take off my mask? Okay, thank you. So, okay, so this work is in collaboration with Dr. Dr. Sang-Yun Lee and Professor Hyuk-Jun Kwon and Professor Hyung-Gyu Park. They are all in KIAS. Okay. So in macroscopic scale, the motion is deterministic. So in such a scale, fluctuation is not important. However, in a microscopic scale, the fluctuation is important. So this is a schematic diagram of a stochastic system I'm interested in. So here, T1 is the initial time and T tau is the final time. And this is the initial state of a system, x1, and this is a final state of a system, x1 prime. So this gamma is a stochastic trajectory. So there are many initial states and there are many final states. So this initial state constitute initial distribution P0 and final states, final distribution P tau. So in this setup, we are interested in measuring some observable theta, and of course, theta is a function of gamma trajectory. So for example, heat and work and displacement, these are kind of observable we are interested in. And one special observable is entropy production, sigma, which is also a function of gamma. So here, our general question is that, is there any general relation between entropy production and measurable quantities? Okay, so for this question, the first one we found is, the researcher found is that a so-called thermodynamic uncertainty relation, and shortly saying TUR. So TUR is a relation between the entropy production and observable, fluctuation of observable. So the TUR looks like this. So here, this is a variance. And so this left term is called relative fluctuation. And so the product of relative fluctuation and entropy production should be larger than some universal value. So here, KB is Boltzmann constant. So, okay, let me give you an example. So this is a molecular, this video shows you some molecular motor motion. So here, let's say that here, let's suppose that the theta observable as a displacement of this molecular motor. Of course, because the motion is stochastic, so this x variable, displacement is also a stochastic variable. So it has a finite variance. So for example, if we want to reduce this relative fluctuation, then from this TUR, we can know that the entropy production should increase. Or if we want to reduce entropy production, then relative fluctuation should increase. So, this TUR is a kind of a trade-off relation. So it means that we have to pay more thermodynamic cost, which is the entropy production, for reducing fluctuation, and vice versa. And the thermodynamic second law only tells us that entropy production should be non-negative. But if we rearrange this TUR, then we have this inequality. Then it tells us that entropy production is larger than some positive number. So this TUR gives us a stronger bound than the thermodynamic second law. And this is the TUR for overdamped Langevin system or Markov jump process in the steady state. But for example, if we are interested in some underdamped Langevin dynamics, which includes other parity variables, then the form of TUR should be modified in such a way. So we need some operator before the average of the observable, and we also have to put some initial Shannon entropy term. Okay, so this is about TOR, but today I'm going to talk about a different type of trade-off relation, so-called speed limit. So the speed limit is about the relation between now the entropy production and the distributions, final and initial distributions. So let's suppose that there is an initial distribution and final distribution. So if we want to move this initial distribution to this final distribution during a finite time tau, okay, so let's suppose such a situation. Then this inequality holds. So the meaning of this inequality is that here tau is a transition time from this initial distribution to this final distribution, and this is entropy production, so their product should be larger than this quantity. So here A bar is a dynamical activity, means that number of transitions, and dTV, this is actually the distance between two distributions P and Q. So here, this is a distance between the initial and the final distributions. I will explain these quantities later explicitly. Okay, so from this inequality, we can now understand this kind of a trade-off relation. So, for example, if we want to decrease total time, then entropy should increase. Or if we want to reduce entropy production for this transition, then transition time should increase. So roughly saying, this is also kind of a trade-off relation. So it means that we have to pay more thermodynamic cost for faster transition. Okay. And conventionally, we write a speed limit in this way by moving this entropy production term to the right-hand side. We conventionally write in this way. Okay, so today I'm going to talk about in the twofold. So in the first part, I will talk about how to derive a general form of speed limit. And in the second part, I will talk about how to apply this speed limit to the finite-time Landauers bound problem. Okay, so first I will talk about the motivation of this speed limit, the study of this speed limit. Okay, so the motivation is actually from the quantum speed limit, which was introduced in 1945. So it was about the closed quantum system. So here, let's say that rho 0 is initial state, and the rho tau is a final state of a closed quantum system. And then this quantum speed limit holds. So this is a transition time, and this L is a kind of a distance between two states. And here, if we take ha bar goes to 0 limit, which is a classical limit, then this right-hand side just becomes 0. So in such a limit, this inequality becomes a very trivial one, which means that transition time is larger than 0. It is a meaningless statement. So the people are asked whether there is a meaningful speed limit inequality even in the classical system. So this is a motivation why people study the speed limit in the classical thermodynamic system. Okay, so in this talk, I will focus on the Markov jumper process. Of course, we can consider Langevin dynamics, but if we consider Langevin dynamics, the speed limit, the distance, we have to consider a different kind of distance, so-called Wasserstein distance. So here I'll only focus on the Markov jumper process. Okay, so here Rnm is a transition rate from m state to n state, and Pn is a probability of state n. So this is a master equation. And then here we are considering this type of entropy production expression. So, this is some general expression. So, so here there is some R star here. So if we choose R star as the original transition matrix, then this is nothing but the definition of original entropy production rate. But if we choose R star in this way, then this expression gives the Hatanosasa entropy production rate. Actually, this corresponds to the excess entropy product and excess entropy production Andreas explained. Okay, but in this talk, of course, our general formalism is applicable to both of these entropy production, but for simplicity in this talk, I will only focus on this original entropy production. So you can think of it R star just as original one. And then here, A dot is called dynamical activity, and its definition looks like this. So it is a summation of all jumps per unit time. So this is a number of jumps rate. And by integrating over time from 0 to tau, then it gives a total number of jumps, right? So it is called total activity. And here A bar is defined as total activity divided by total time. So it is mean activity. So this A bar here, so the meaning of this A bar is mean activity. And finally, here, this distance is called total variation distance. So the definition looks like this. So it is about the distance between two distributions P and Q. So when the two distributions are exactly same, then it becomes 0. So in such a case, this value becomes 0. And when the two distributions are, completely different, then it becomes 1. So the total variation distance is in between 0 and 1. Okay. And for simplicity, I will use the notation L instead of this DTV and some complicated notation. So we can simply write the speed limit form in this way. Okay, good. So this form actually discovered by these groups. So this is actually previous form, but in this talk I will introduce a more general form of speed limit. It looks like this. What I mean by general is that the previous form can be derived from this general form. Okay, so to derive this general form of speed limit, then we need, need this key relation. So the meaning of this key relation is that there exists some convex function h which satisfies this inequality. I'll show you the exact form of the convex function h later, but here at this moment, let's accept first this inequality. Then it is easy to derive from here to there. So by dividing the same number to both sides of this inequality, then now here let's define function g of x in this way. Then you see that this left term is actually the same form of this g of x with the argument this x. And then by taking the inverse function of g, then we can show this inequality. And now we use this definition of a total activity. Then we can simply show this general form. So now we know how to go from here to there. So the remaining part is to know how to derive this key relation. Okay, so this is a total variation distance definition, and we can show that this total variation distance is smaller than this equation. You can, this is, the straightforward. And then here I will use some definition. So, I will define Q and Q tilde here, and this Q is, related to this first term, and Q tilde is related to this second term, and divide by this A dot. Actually, this A dot is dynamical activity, and this is actually the normalization factor. So it means that Q and Q tildes are normalized quantity. So that's why we can regard Q and Q tilde as a probability. So by using this definition, when we can convert this equation from this equation to this equation. And then here, because Q and Q tildes are two different probability, then now by using the definition of a total variation distance, that we can write this part by using the definition of a total variation distance in this way. Okay, that's good. So here I will use some important property of the statistical distance. So as I explained that, this is a total variation distance, and it is in between 0 and 1. And when the two distributions are same, it becomes 1, and they are completely different, then it becomes 1. Okay, then the second one is a Kullback-Leibler divergence. Of course, this is not the distance, but it can be used as a kind of a distance between two distributions. So for these two distributions, P and Q, this is a definition of a Kullback-Leibler divergence. So when the two distributions are exactly same, then it becomes 0. But the Kullback-Leibler divergence does not have upper bound, so it can diverge. So the important thing is that between these two things, total variation distance and Kullback-Leibler divergence, there is an important relation between these two. So there exists some convex function h which satisfies this inequality. Now, I'll show you the explicit form of this convex function later, but here, okay, then let's first accept this inequality. And then by using this inequality and taking the inverse function of h, we can write this inequality. And now then we can calculate what is a Kullback-Leibler divergence by using these two definitions, Q and Q tilde. So this Kullback-Leibler divergence is nothing but the entropy production rate divided by dynamical activity. So, and it has one more important property. So you can easily check that the Q and Q tilde is same as the Q tilde Q. So you see that this is exchanged, the order is exchanged. But in general, the Kullback-Leibler divergence is not symmetric. But in our case, in our special case, you can see that they are symmetric. So I will use this symmetric property later. So please remember this symmetric property here. Okay, so by plugging this equation into this one, then we can show this. And then by using the Johnson's inequality, then we can show that this one is smaller than this one. So this total variation distance is smaller than this quantity. So that's why, this key relation holds. Okay, so now we know how to derive this key relation. So finally we derive this general form of the speed limit. Okay, then let me show you the explicit form of the h function here. So the first, the simplest one is a Pinscher function. So it 2x squared. So for example, let me give you an example. So these are two distributions, P and Q. So let's say that P is 0 and 1, and Q distribution is 1 and 0. Then we can simply calculate the total variation distance. So it becomes 1 in this case. And in this case, Kullback-Leibler divergence diverges because of this term. So using these two quantities and by using also this Pinscher function, we can simply check this inequality hold. because the left-hand side becomes just number 2 and right-hand side becomes infinity. So this inequality holds. Even though this inequality holds, but very, loosely hold, because the left-hand side is just a number 2 and right-hand side infinity. So it means that when d is close to 1, then the Pinscher function gives a very loose bound. But the meaning of the d is equal to 1 is that two distributions are completely different. When d is close to 0, which means that two distributions are very much the same. And then when the two distributions are very much the same, then Kullback-Leibler divergence also close to 0. So in this case, then the left term becomes close to 0, the right term also becomes close to 0. So in such a case, this inequality now becomes tighter than the previous case. So the Pinscher bound gives a tighter bound only when d is close to 0. Then what it means? So we are considering these two distributions. Actually, this is a P and Q. The meaning that two distributions are very much the same, it means that this is the forward path probability kind of, and this is a backward path probability. So their ratio becomes very much, their ratio becomes 1, close to 1 in this case. So it means that the dynamics is nearly reversible. However, in this case, the two distributions are very much different. So it means that the forward path probability and backward path probability are very much different. So it means that the process is highly irreversible. So it means that Pinscher bound gives a very loose bound for highly irreversible process, but it gives a tight bound only for nearly reversible process. So to improve this, the looseness of this Pinscher bound near d equal 1, we can use other functions. For example, a Bragg-Hoover function or a Gilardoni function. These are, they have been studied in information science. So this is a plot for these three functions. So x-axis is total variation distance, and y-axis is h function. So you see that this blue curve is a Pinscher function, and this is a g and bh function. It looks like this. So you see that at d equal 1, so the Pinscher function gives a finite number, but these two functions diverges. So it can give a tighter bound than the Pinscher function near d equal 1. So, but we can use additional, if we have this additional condition, then we can use tighter bound. So if the Kullback-Leibler divergence are symmetric, then we can use this the tightest function. So you see that this pink line is always tighter than other functions. But as I mentioned that in our case, the Kullback-Leibler divergence is symmetric. So we can use this tightest function. So for example, if we use this Pinscher function, then h is 2x squared, then this is, if we just plug this equation, then gx function is simply becomes x identity function. So by applying this one, then we can easily get this this speed limit bound. Actually, this form is correspond to the previous speed limit form. So it means that this one is tight only for nearly reversible process, but it becomes very loose for highly irreversible process. However, if we use this tightest bound, then we get this speed limit, and I will call this one as a symmetric KLD bound. then actually I will show you the example. Then this is tight for every time. And let's compare with the speed limit to the given by Andreas. Actually, he uses some function distance as a Wasserstein distance. You can see that actually the forms are exactly the same. Okay, so we can apply this speed limit to the problem of Landau's bound problem. So Landau's bound problem, so what is a Landau bound? So it is about for erasing one bit of information, at least kBt log 2 heat should be dissipated. And this minimum bound, minimum heat, is attainable only in the quasi-static process. So for a finite time erasure process, then some additional cost is necessary. And from this series of studies, people understand that this additional cost is proportional to 1/tau. Here, tau is a erasure time. So when tau goes to infinity, then this term vanishes, so we can attain this minimum bound. Actually, tau goes to infinity limit is a quasi-static limit, so that's why we can have this minimum bound. However, when tau goes to 0, a very short time, then actually it diverges in this way. So, what is the meaning of an erasing process? So let's say that there is a one memory here. It has a two states, so 0 state and 1 state. And in this example, because system is in 0 state, we read this memory as in 0 state. And let's say that there are many memories here. So this is 1, 1, 0, 1, 0. So for example, let's say that initially, for a probability for observing 0 state is half, and probability for observing 1 state is half. So initially, half have a probability. But erasing process is nothing but the reset to 0 state. So after erasing process, final state will look like this. So the probability for observing 0 state is 1, and the probability for observing 1 state is simply 0. So it means that erasing process is nothing but the distribution change. Initially, half a probability, and finally a 1/0 probability. So that's why we can apply speed limit theory to this erasing problem. So we can easily calculate the total variation distance between two distributions, and then we can also easily calculate the Shannon entropy change of these two distribution, which is minus log 2. So this is a speed limit I showed you, and by rearranging the terms, we can have this relation. Entropy production is larger than some quantity. And then we know that entropy production can be divided into two parts, the Shannon entropy change plus reservoir entropy change. So by plugging this equation into this inequality, then finally we have this relation. So this is actually the finite-time Landauers bound. So this is a minimum dissipation, kBt log 2, plus something else. This is the additional cost. So the function g, the meaning of the function g is actually it gives an additional cost. So for example, if we use a Pinscher function, then this additional cost becomes this one, and you see that this is proportional to 1/tau, and this corresponds to the previous studies result. However, if we use some tightest bound, the symmetric KLD bound, then we have this additional cost, this one. Okay, so let me show you how tight this bound is. Okay, so we can consider two models. So one is a discrete 1-bit model, and the second one is a coarse-grained bit model. So in this model, there are two states. So let's say that initially the system is located in one state, and by raising the energy state, then we can move the state from one state to the 0 state. So in such a way, we can erase the memory. And in this second model, this is actually the overdamped Langevin system, and we use some symmetric potential, and by applying some asymmetric potential, we can we can move the particle from one state to zero state. Here, I mean, this is a coarse-grained model because the zero state or one state has actually infinitely many micro state here. Okay, so this is a calculation result of this discrete model. So x-axis is and y-axis is entropy production, and x-axis is inverse of V, and V is defined in this way. And this is a plot for Pinscher function bound and symmetric KLD bound plot. So you see that when V equal to 1 here at this point, the Pinscher bound orange line has a finite value, while the symmetric KLD bound diverges at this point. Actually, this regime is about the highly irreversible process regime, and this regime is nearly reversible process regime. So if we magnify this plot, then this is a magnified view, then you see that, so at this point, the Pinscher bound gives us a finite number, and symmetric KLD bound diverges, so it means that Pinscher bound is infinitely loose compared with the symmetric KLD bound near the highly irreversible process. But you see that this symmetric KLD bound actually really tight. It touches the bottom of this data point. And actually we can find some conditions for optimal protocol which really touches this symmetric KLD bound. And this is what I mean by tightest. It cannot be better than this symmetric KLD bound. And this is a sufficient condition for this optimal protocol. And finally, even though I started from the Markov jump process, discrete state, but it can be applied to this coarse-grained beam model. So these green dots are simulation data from this coarse-grained beam model. You see that it is always above this bound. But there is some gap here. So actually this gap originates from the coarse graining of this model. Okay, so let me summarize. So we studied the speed limit, and we derived the general form of the classical speed limit, and we apply this speed limit to the finite-time Landauers bound problem. So, okay, so we found that it is really, it gives the tightest bound. Okay, thank you for your attention.
Thanks for the nice talk. Okay, you're first. I understand from your plot why you call it tightest bound, but from the derivation, it looks that in principle there might be even tighter bounds, because you say, okay, this function is better than the other, and so on, and you arrive. So, do you have a mathematical proof that you cannot do anything better than that, or it is experimental?
Oh, okay. So this is symmetric KLD bound. I mean, it is about. I mean, yeah, okay. It is about. I mean, this tightest bound, and then we can show that for two-state model, then we can show that this is the tightest. And then for more than 3 or 4 state model, then I don't know how to show that this is the tightest. So yeah, in such a way, in our model, I mean, actually the Landau bound Landau problem is actually a two-state problem. So we can, yeah.
Any further questions? Okay, seems not. Let's thank our speakers again.